Welcome back to ECE 442-542, the lecture prior to spring break. You wouldn't know it by the large attendance in the room, but we'll proceed. At least I have a few smiling faces. Maybe they won't be smiling for long, but especially after the announcements. So let's get into the announcements. Homework number 4 is due the day you return from spring break. And I've tried to give you some additional material to help you with that since you have some extra time between now and then. In particular, lectures 4.2 and 4.3 are not going to be held in this room. They are already available to you, and those deal with zero-order hold equivalents. There's one, the 4.2 talks about zero-order hold equivalents by hand or performing it by hand. The other one is zero-order hold of a state space system. And you'll need that for these various problems that I've tried to indicate. So if you're reading through those problems and you go, I have no clue what he's talking about, hopefully these extra videos will help. We will have a review session the day we get back, and hopefully it will occur as before at 7 o'clock in this room after our normal lecture. And if you have questions concerning material for exam number 2, you can submit those in the quiz section that's been designated for that very purpose. You can simply type in or scan in what you have for questions. And exam number 2, is that a couple of weeks from today? That's on the 13th of March on a Wednesday. I have made your project information, if you're in the graduate section, graduate level section, that's available now. It's at the bottom of the content page. There's a write-up on your project. There's also a table of zero-order hold equivalents in that lecture 4.2 that I've tried to just create. So if you want to say, oh, what happens if I take the zero-order hold equivalent of this or of this? There's a few rows that hopefully now give you this side-by-side comparison of what you might need or be interested in for zero-order hold equivalents. And that particular lecture, 4.2, derives the zero-order hold equivalent of an integrator. Last time we derived it for a constant, and what else did we derive it for? Do you remember? A pure mass system. So a second order system, now the integrator is sort of in between those two extremes. And there is then the derivation of the zero-order hold equivalent of a state space in lecture 4.3. Today's lecture is actually 4.4, if you're keeping track. We did 4.1 on Monday. Now you've had 4.2 and 4.3 provided offline. I guess I should say online. And now we're doing 4.4, which is dealing with discrete equivalents, not zero-order hold equivalent, but discrete equivalence without using a preceding hold operation. And we'll do that a couple of different ways, or main ways: numerical integration and pole zero mapping. With numerical integration, we will actually do it 3 different ways. We'll do it with forward numerical integration, backward numerical integration, and trapezoidal, or maybe you've heard of bilinear transformation. And last time I mentioned that you can't just replace S with Z to get the discrete equivalent, but in fact, using these numerical integration strategies, you can replace S with certain formulas involving Z, and I've indicated what those are in red. So if you do a forward numerical integration discrete equivalent, if you have a transform expression in S, you can simply, everywhere you see an S, you can replace it with that expression, Z minus 1 over T. And it sort of makes sense. Remember the association we had with s equal to 0 and z equaling 1. So you can see that when the left-hand side goes away, when z is equal to 1, that's consistent when the right side goes away when s is equal to 0. There's this sort of equivalence relationship between the s domain and the z domain. We also have, I know it's hard to find a chair, but see if you can squeeze in somewhere here. I don't have my glasses, so it's going to be hard for me to find an open chair. Where were we? Oh, with the different numerical integration strategies. We'll go through that today, and we'll hopefully get into the pole zero mapping. But the pole zero mapping is really, where do you map your zeros? So this s plus a factor actually maps to a factor that looks like z minus e to the minus at, and so really we're replacing s in this z equal to e to the st with where that pole is located. Or I'm sorry, that 0 is located in this case, which is at minus a. Similarly for the poles, we map those through this mapping, z is equal to e to the st. We also will talk about zeros at infinity. Have you heard of zeros at infinity before? If not, that's okay. It's not a hard concept. Zeros at infinity are really the number of, or how many fewer zeros you have, finite zeros, than you have poles. In this g of s expression, the order of the numerator is 1, the order of the denominator is 2. You have a pole zero excess of 1. And in fact, you have 1 0 at infinity. If you looked at this ratio as s goes to infinity, then you really look at s over s squared as s gets big, and that now looks like a 1 over s, so you have 1 0 at infinity. If s goes off to infinity, this g of s expression vanishes. If we just had k in the numerator, then we would have 2 zeros at infinity. What I'm trying to then get to is in the pole zero mapping, we put factors equal to z plus 1 into that expression with the power associated with the number of zeros at infinity. In this case, we have 1 0 at infinity, so we have 1 factor z plus 1. There are ways of modifying that, and we'll get into that for implementation reasons, when you might want 1 fewer factor of z plus 1 than you have zeros at infinity, just so that it is a more realizable implementation in the discrete setting. We'll go over that as we get to it in the pole zero mapping. But today we are focused on scenario number 1, discrete equivalence without worrying about a preceding hold operation in front of those frequency domain transforms. Here is the analog system and its discrete equivalent buddy. Here we're simply trying to replace c of s with c of z. How do we make that connection? How do we generate a c of z from a c of s? In scenario 1, we are not incorporating a hold device, and we're really just looking at this type of a equivalent operation. Up top, you have the continuous time. Input and output are connected by a transform or a transfer function c of s. We want to know now, if we went into the discrete time, how would we create an equivalent c of z to give us similar behavior in the discrete time setting that we're getting in the continuous time setting with c of s. How do we come up with a c of z from a c of s? And I've already given you the answer in basically the goals section of today's class. But let's now look at how we can do that in two different main ways. Pole zero mapping is the second way. The first way, which is what we're probably going to spend most of our time on today, are the numerical integration strategies. And we can find these numerical integration approximations using a forward approximation, a backward approximation, or a trapezoidal approximation. And you might not see it stated as trapezoidal, but you might see it as bilinear. So it could be referred to many different ways: trapezoidal, bilinear, but the third one that we will talk about is the trapezoidal. And the trapezoidal makes more intuitive sense the way that we're talking about it today, in terms of a numerical integration approximation, or an approximation to integration. Here's the picture that we want to focus on. We have a function, x of t, that's the blue line, and the area underneath that is obviously the integral of x of t. We want to know, how can we create a discrete time approximation to finding the area under that curve? Or what is y of t? Y of t is what we're referring to as the area underneath that curve, or the integral of x of t. So let me just write that down. Here's the picture, and you can see that I've indicated a couple of different time instances on that plot on the horizontal axis. I've indicated our final sort of shaded location, which I've labeled as little t, and behind that, one sample period before that, I've now identified the point little t minus one sample period capital T. And if you're paying close attention, maybe you can see that I've actually shaded this with two different colors, and the difference, or the area between t minus capital T and little t, is not cross-hatched, it's just shaded. I'm trying to now focus on that little sliver of area in this discussion of numerical integration. That's what we're going to be focused on, or concentrating on, in order to develop these expressions for a discrete time version of this area under the curve. Let's establish some notation. Y of t is the integral, let's say from 0 to t, of x of tau d tau. And we can write that actually other ways. But for starters, let's just recall what we're saying y of t is. Y of t is the area under the function x of t up to time little t. If that's y of little t, then y of little t minus capital T, or y at one sample period before y of t, this then is the area under x of t up to time little t minus capital T. And that should be what I'm trying to illustrate here with the black slashes or shading for y of t and the blue shading for y of little t minus capital T. That's the distinction I'm making. Or if we wanted to write that in another way, this expression for y of t, we could say, oh, that's equal to y of t minus capital T plus the area under x between t minus capital T and little t. And this rightmost term is really the single shaded area between little t minus capital T and little t. And we want to now develop different ways of approximating that little area or that sliver of area between little t minus capital T and little t. Let's do it then by defining, or basically chopping up our time axis into sampled slivers. Or let's let little t be little n capital T in terms of that's n samples in to this process of slicing up our time axis. Replacing little t with little n capital T in this integral expression that I just wrote down says that we now have y of little n capital T equaling y of the quantity little n minus 1 times t plus the integral from little n t minus t all the way up to little n t x of tau d tau. And what distinguishes each of these different numerical integration strategies or techniques is related to how we make this approximation of this rightmost integral expression. They're the same up until that point because we're just adding a little bit more to what y was at one sample period before little t to get y at little t or at nt. The different numerical integration techniques are in fact based on how we approximate this integral. Let's look at the first one. We said we were going to call one the forward rule for numerical integration, and now what we want to do is simply approximate the integral with the rectangular area looking forward. There's where the name comes from. Looking forward from the value of x at that sample period, one sample period before little t, or n minus 1 times capital T. Or if we go back, what we're saying is now we are approximating that area with this rectangle. We're saying let's look forward in time from x at time little n minus 1 times capital T and just approximate that sliver of area with this rectangle. that allows us now to write it as follows. We have this integral from nt minus t to nt x of tau d tau. If we're approximating it in that way, what's the area of that rectangle? It's just length times width, or width times height in this case. The width of that rectangle, this is now little n capital T. This is little n t minus t. Or it's now this distance between those, nt minus t, and that gives us t. The width is now just the sample period. And the height is just the value of our function x at the left point on that x of t function. That's now the way that we will numerically approximate or perform this numerical integration with the forward rule. Or we can now say that y at time little n capital T is approximately y of n minus 1 capital T plus the approximation of the integral, which is t x of n minus 1 t. And now that we have this skill of going from time domain to frequency domain, let's go into the frequency domain, or transform this time domain difference equation, put it into the frequency domain. If we now go into the transform domain, what does that equation look like in the frequency domain, the z domain? What's the z transform of y of n, or y of n capital T? That we just say, oh, that's the z transform of y of n, which is capital Y of z. The left-hand side now is just capital Y of z. If that's the z transform of little y of n, what's the z transform of y one sample period before that? That's now where we can use our operator z to the minus 1 times capital Y of z. And finally, we can do the same thing with x. It's now delayed by 1 from t, or little n capital T. This is now t z to the minus 1 capital X of z. Everybody comfortable with that? Moving from the time domain to the frequency domain. I need to get out from underneath the speaker because I'm getting feedback. Now let's just do some manipulating. Suppose we now combine our y terms. Or now we can find the transfer function between the input z transform, which is capital X of z, and the output z transform, which is y of z, or y of z over x of z is equal to t z to the minus 1 over 1 minus z to the minus 1. Or if we multiply that by 1, z over z, we end up with t over z minus 1. And that's now the transfer function between the input x, that's the function x, and the output, which is the integral of that, which is y, is now t over z minus 1 when we're using the forward rule of approximation. What we want to do is relate that or connect that with the analog case. Let's now recall what we have in continuous time or in the analog case. In the continuous time, we have y of t is equal to the area underneath the curve, where the curve is x. What if we now take that into the frequency domain and the s domain? If we Laplace transform that time domain equation, we then have for the left-hand side simply y of s. And what's the Laplace transform of an integral? Or what's the integral operation look like in the s domain? It's just the reciprocal of what the derivative looks like, and the derivative is a multiplication by s. The integral is now a division by s. So now we have 1 over s x of s. And now we can find the transfer function between x and y. We have y of s over x of s is 1 over s. To establish the relationship or make the connection between the s domain and the z domain, we can compare this 1 over s with what it looks like in the z domain, t over z minus 1. Or comparing the transfer functions, we can now say, oh, here's what it looked like in the s domain. That was 1 over s. In the z domain, it looked like t over z minus 1. There's the connection. Or maybe it's not as straightforward to always be talking about reciprocals of s. We can now invert both sides, and we can say, oh, the relationship between the s domain and the z domain using the forward rule of numerical integration allows us to say, oh, wherever we see an s, we can replace it with this factor z minus 1 divided by t, and we can now generate an h of z from an h of s. Or we can replace s with z minus 1 over t in h of s to actually obtain the h of z. Let's just look at a very basic example of this. Suppose that we now say for a S domain transfer function, let's look at a low-pass filter. We know the characteristics of a low-pass filter. Suppose we now say that h of s is a over s plus a. In our analog setting, where's our pole? And this is not difficult. That's at minus a. There's the pole of our low-pass filter. Do we have a finite zero? Do we have a finite value of s that causes h of s to vanish or to equal 0? No. So there's no finite zero. And what's the DC gain of that low-pass filter? Or how do we find that? What's DC in the frequency domain? What value of S? 0. So now we can evaluate h of s when s is at DC or at 0, and we have a over 0 plus a, which is why I had a in the numerator to begin with. I have a over a, or the DC gain, is 1. Which means if we have a DC gain applied to that analog filter, we'll get that same constant out. Let's now use this forward rule that we just created, the forward rule, to find h of z. And let me now call that h sub f of z, since we'll have several of these numerical approximations to play with or to derive. Now what we said we could do is we could take the original h of s, and everywhere we see an s, we simply replace it with z minus 1 over t. Or that now becomes a over z minus 1 over t plus a. And we can clean that up a little bit if we multiply by 1. Or now our h sub f of z, our discrete equivalent of a low-pass filter using a forward numerical integration approximation strategy, will now produce a filter in the discrete time setting of a t over z minus 1 plus a t, or a t over z minus 1 plus at. What if we look at some of the same features in the discrete time setting that we looked at in the continuous time setting for the filter's behavior? What about the poles? Where's our pole in the z-plane? Poles in the z domain are the same, or found the same way as the poles in the s domain. We simply say what values of z cause the denominator to vanish. That will now be 1 minus at. Our pole is now at 1 minus at. It's going to depend on the choice of t and the original bandwidth of our low-pass filter. And where is that relative to the unit circle, which we could think of for stability purposes of this filter? This is inside the unit circle, and how far in depends on how big we make capital T relative to the original bandwidth of A. What about the zeros? Do we have any finite zeros? That seems consistent with what we had in the analog case. And what about the DC gain? What value of Z corresponds to DC in the Z domain? Now Z is equal to 1 is our DC frequency. So now we say, oh, let's look at that when Z is equal to 1. We now have AT over 1 minus 1 plus AT. Or we now have a consistent DC gain. We have a gain of 1 in that discrete approximation. That's an illustration of the forward rule of approximation for the numerical integration strategy. We have other ways of approximating that little sliver beyond little t minus capital T and little t. What if we now looked at the backward rule? We'll say that's B In this case, let's approximate that integral between t minus capital T and little t with the rectangular area looking backward from now the right point, the point on the right. Now what we're doing back here not sure what color to use since I don't want you to get confused with red and green. So what color do we like? Let's do purple. There, that's really distinctive, isn't it? But now do you see the area that we're using now in this approximation? We're looking left or backward in time. We're going from little x of nt back to the left, and that's now the way that we are approximating this little sliver of area. For that case, we now have this integral from little n capital T minus capital T to little n capital T of x of tau d tau. We're now approximating that to be, it's the same width, capital T, but now the height is little x at the rightmost endpoint, nt. And you know the drill. Now we can say that in the time domain, if we wanted to find an approximation, we would say, oh, the area under the curve at time little n minus 1 times capital T, or we could write that as little nt minus t plus t times x of nt. Going through similar steps that we've already done for the forward rule, if we take this into the transform domain, we have y of z is now going to equal z to the minus 1 y of z plus t x of z. Or our transfer function y of z over x of z is now t over 1 minus z to the minus 1, or multiplying both top and bottom by z, we now end up with t z over z minus 1. And we can do what we did before. We can compare the transforms between the S domain and the Z domain. S domain was simply 1 over S, and now we're associating that with TZ over Z minus 1. Or S is now going to be replaced with Z minus 1 over TZ. To do the backward numerical integration strategy, we replace everywhere we see an S with a slightly modified Z expression. It's now Z minus 1 over TZ in the original transfer function h of s to obtain h of z. For consistency, let's go back to the same original low-pass filter that we had before, which was A over S plus A, but this time let's apply the backward rule of numerical integration approximation strategy, or h sub b of z is now going to be h of s, with s being replaced with this ratio z minus 1 over tz. We now have a over z minus 1 over tz plus a. Now to clean it up, let's multiply by 1 that looks a little different. Let's make our 1 be tz over tz. And h sub b of z now becomes atz over z minus 1 plus atz. Or that's now atz over 1 plus at times z minus 1. In this approximation, where is our pole? We find the pole the same way. We set the denominator equal to 0, and that's now going to be 1 over 1 plus at. Where is that relative to the unit circle? A is the bandwidth of our low-pass filter. Capital T is our sampling period. AT is probably going to be a small number. We add it to 1. That gives us something bigger than 1, which we're dividing into 1. We now have some value a little bit less than 1. Again, it's inside the unit circle, but it's not in the same location as our forward rule was. Our pole is a little different. This is a slightly different numerical integration approximation strategy. Where is our finite 0? Or do we have a finite 0? We now have a 0, a finite 0 at the origin. We didn't have one before. What about the DC gain? Again, we evaluate h sub b of z at z equal to 1. And that's now at times 1 over 1 plus at minus 1. So our DC behavior is the same. We have a DC gain of 1. I know you're having a lot of fun with this, so let's keep going. Let's look at another way of approximating that little sliver. And this one, let's get a little bit more creative and not do a rectangle. Let's do a trapezoid. Let's now basically do the average between the left endpoint and the right endpoint, or do a trapezoidal approximation of that little sliver. So strategy C is now going to be using the trapezoid rule. Where we want to approximate the integral by a trapezoid. Or this integral from nt minus t to nt of x of tau d tau is going to be what? What's the area of a trapezoid? Do we remember? Or we could just draw a picture. I'm not even sure how it was. Was x of nt bigger than x of nt? Wow. Yes. So now let's just sort of remind ourselves of what we have. Maybe we'll do it in a little bit. Couldn't we say that it's basically now a rectangle and a triangle, if we wanted to think of it that way? And so if we add those pieces up, we actually see that the width is still t for both. And I'll leave it up to you, but essentially we average the two heights, and that's the effective height of this trapezoid in terms of the area. So look at 1/2 base times height of the little triangle that you're adding, and the height that you're, and the width of the rectangle, and you'll end up with x at nt minus x of n minus 1 cap t all over 2. That's now how we will average those. And if you look at this, isn't this sort of like averaging the first two strategies? We had the first one, and we had the forward, we had the backward. Now we're basically, would you guys wake me up? That's a plus. We want to take the average of those two endpoints. It's x of nt plus x of n minus 1t, and this is like averaging forward and backward. Or in our difference equation, we now have y of nt is approximately y of nt minus t plus t over 2 x of nt plus x of n minus 1 cap t. We can transform that or take it into the frequency domain. We now have y of z is equal to z to the minus 1 y of z plus t over 2, and really we just have 1 plus z to the minus 1 capital X of z, by z transforming that approximation term. Or we can now solve for this transfer function, y of z over x of z is now t over 2, 1 plus z to the minus 1 over 1 minus z to the minus 1. Or if we multiply again by 1, z over z, and just put in front capital T over 2, we now have z plus 1 over z minus 1. And if we compare the transforms, we have our S domain, that's still the same, and our Z domain now is a little different. Our S domain is 1 over S, and we're going to relate that to capital T over 2 times Z plus 1 over Z minus 1. or in terms of an unreciprocated s, it's now s is 2 over t times z minus 1 over z plus 1. Now if we want to use the trapezoidal rule for numerical integration, we now replace the s with a little bit more involved expression, 2 over capital T z minus 1 over z plus 1 in our transfer function h of s to obtain h of z. And now I know you're just anxiously awaiting what this looks like for a low-pass filter. This is now for the trapezoid rule, or you might see someone else or a source call it the bilinear transformation. Applied to the same low-pass filter, which is A over S plus A. And I'm going to stick with the T for trapezoidal rule for my subscript since we've already used the B for backward. I'm going to say now H sub T for the trapezoidal approximation is now H of S with S equaling or replaced with 2 over capital T z minus 1 over z plus 1. Or I now have A over 2 over T z minus 1 over z plus 1 plus A. Let's get really creative with our 1. Let's say that that's T z plus 1 over T z plus 1 to give us a ratio of polynomials in z, so that we now have A T z plus 1 in the numerator, and we have 2 times z minus 1 plus A T z plus 1. Combining coefficients of powers of z downstairs, we now have 2 plus AT z plus AT minus 2, and upstairs we still have AT z plus 1. Where's the pole using the bilinear or the trapezoidal? We set the denominator equal to 0 and solve for z. And now let me insert the negative sign in my numerator. So I'll now say it's 2 minus AT over 2 plus AT. Where's that? AT is a positive value. It could be small, but now we're subtracting it from 2 upstairs and adding it to 2 downstairs. So again, that ratio is less than 1. So that makes us feel okay. Where's our finite 0? That's now different than the other two. Now it's at minus 1. So that's really fast if you wanted to think about it in terms of speed in your z-plane. Z equal to minus 1 is a very fast location. What about the DC gain? Again, we set z equal to 1. And what do we have upstairs? We have 2 times AT. And downstairs we have 2 plus AT plus AT minus 2. The 2's cancel, and we're left with the same expression in the numerator as denominator, so we're now dealing with, again, a DC gain of 1. Now I mentioned something about speed or fast pole. What if we look at the following? Here's our z-plane, and I've now tried to superimpose on that the upper half of the unit circle. And suppose I put a couple of poles. Which of those poles is the dominant pole? Or which is, and when I say dominant, is that the fast or the slow pole? What pole based on this, and if you're having trouble, I would just insert some generic numbers. I would say, oh, that one on the right is at 3/4 and the other one's maybe at 1/4, just to give us something to think about. And now when I say dominant, or if I say 3/4 and 1/4, do you see the modes? Now you have a mode at 3/4, which 3/4 gets raised to the n, and you have another mode at 1/4 raised to the n. Which of those is the faster? Which one decays most rapidly? The one at 1/4. This particular pole then is the fast pole. This one must be the slow pole. So which one is the dominant pole? By dominant, I mean which one dominates the behavior in the time domain. That's the slow one. That's the one that dominates. So your slow one's the dominant pole. And we're actually going to start looking at frequencies on the real line, but also frequency response along the unit circle. Meaning, we now have this relationship of z is equal to e to the st. And if we were interested in the frequency response in the s domain, what do we do with s? Or where are we in the s plane for our frequency response? If I had a transfer function h of s, and I said, what's the frequency response of that low-pass filter, how would you give me, or what would you do to produce the frequency response? Would you say, well, I would give you the Bode plot. That's the frequency response. And what's the Bode plot? Well, now you're interested in h of j omega. Or you're really saying, what is the behavior of this transfer function as omega goes from 0 dc up to infinity? And in fact, that now says that you're playing or evaluating this transfer function along the imaginary axis. Here's j omega, and here is real s. If that's now our frequency response, when we say h of s with s equal j omega, if we now use that in h of z, we're replacing s with j omega, and what was z? It was that. And now we're replacing S with j omega, so that now we have this H evaluated at e to the j omega t. Where are we evaluating that H? If we're evaluating it at e to the j omega t, e to the j omega t has a magnitude of 1, so now we are actually evaluating that along the unit circle. That's our frequency response. And now this doesn't go from DC up to infinity, does it? Because we've now sampled. We go in the S domain from 0 to infinity. Now we don't go that far. We now have a sampling frequency, omega sub S, and that is now 2 pi f sub s which is 2 pi over t. And what happens when we look at e to the j omega? How do I want to say this? What if we now looked at e to the j omega when omega is equal to, let me sort of forecast the point I want to find. Suppose we look at half the sampling frequency for our value of omega. And this is now e to the j omega t. This now becomes e to the j. We replace omega with omega sub s over 2. But omega sub s is 2 pi over capital T. And where did we end up? 2's cancel, t's cancel, and we end up at e to the j pi. Where is that point in the z-plane? What's its magnitude? Where is it from the origin? It has a magnitude of 1, doesn't it? What's its angle? Pi, or 180, or minus 180. So this point right here is when omega is omega sub s over 2. And that's the highest frequency that we see in our sampled or our discretized system. So we go from DC, which is z equal to 1, all the way around the unit circle, half of the unit circle, and get to omega sub s over 2. All the other points down below are simply conjugates, and so those look like from DC to minus e to the j pi. So that's just the conjugate points. The highest frequency we can really see is omega sub s over 2, and that's where this Nyquist, you could think of, is coming from. The Nyquist frequency is half your sampling frequency. How fast do we typically sample in this class? 30 times. So we're sampling much better or more than what we will in our particular extreme frequency that we can see. That's now our discrete equivalent without a preceding hold device using numerical integration approaches. Let's look at the second one, since I know you want to be looking at homework over the next little bit. Let's look at pole zero mapping, which is on the homework and on the second exam. And this is a pole zero mapping discrete equivalent. Let me try to give us the idea. The idea is that we use this relationship between S and Z to give us another way of mapping from points in the S plane to points in the Z plane. The first step is we map poles of H of S to poles of H of Z, and we do it using this relationship of Z is equal to e to the st. So if we had a pole at -6, we would find a pole factor in the Z plane corresponding to Z minus e to the -6t. Or if we now had this H of S of A over S plus A, where's our pole in the S domain? That's at -A. We now go through this mapping. Z is equal to e to the AT, which if we replace S with -A, we have Z is now e to the -AT, and in our Z domain version, we would now say, oh, this is Z minus e to the -AT. I now have a pole when Z is equal to e to the -AT, and we'll have to worry about what the gain constant would look like. So we map poles of H of S to poles of H of Z. We do the same thing with our finite zeros. Let me just say now we map zeros, and these zeros include finite and infinite, but we map zeros of H of S to zeros of H of Z. And if we have infinite zeros, those get mapped to Z plus 1 factors in the numerator. If we had 1 0 at infinity, if we had two poles and 1 0, we would have 1 0 at infinity. We would then include in our numerator expression a Z plus 1 factor. If we had two zeros at infinity, we would have a Z plus 1 factor squared in our numerator, in addition to any of the zeros, finite zeros, that get mapped to their appropriate factors. Finally, we match the gains. We match the gains of H of S and H of Z. And where we match those gains may depend on what the frequency behavior of that H of S is supposed to be. If it's low pass, we might want to match low frequency gains. If it's high pass, we might want to match high frequency gains. And where's high frequency in the Z plane? You could consider this to be high frequency, -1. So you could let S go to infinity, or omega go to infinity, and map that to -1 when Z equaling -1. Let's look at what it does for low frequencies. Suppose we now had H of S. Well, at low frequencies we would say DC, and then we would match that to H of Z when Z is equal to 1. Suppose now we looked at this H of S equaling A over S plus A, the low-pass filter. If we now do the pole zero approximation, what does that look like? What's in the denominator? Our pole is now at e to the minus at, so we have a factor z minus e to the minus at. Where is that relative to the unit circle? At is a small positive number. E to the minus, that's going to be close to 1, isn't it? So now again we have a pole on the real line close to 1 using this pole zero mapping approach. How many zeros at infinity do we have in h of s? How many more poles do we have than finite zeros? We have one pole. How many finite zeros do we have? 0. So we have a pole zero excess of 1. We have 1 0 at infinity, and we said, oh, for now let's agree that that means that we need to put a z plus 1 factor in the numerator expression for our pole zero matching strategy. But now we have to figure out what k is. And if this is a low-pass filter, how would we pick k? Or what's the low-frequency behavior of h of s? What's its DC gain? It has a DC gain of 1. Can we make the DC gain of h sub pz have a DC gain of 1? Yes, that's how we'll pick k. So let's say now we have a DC gain equaling 1 as our goal. Now we say, okay, h of pz of z, when z is equal to 1, we want that to equal 1, or that's now equal to k. What's upstairs? Well, we're replacing z with 1, so we have 1 plus 1. Downstairs we have 1 minus e to the minus at. Now we solve that for k. K is now equal to 1 minus e to the minus at over 2. And now we have our discrete equivalent using a pole zero matching or mapping strategy for a low-pass filter. We now have h of z corresponding to our k, which is 1 minus e to the minus at over 2 times z plus 1 over z minus e to the minus at. Now we already have designed it for this purpose, but let's just double check our thought process. Where's the pole? It's the value of z that causes the denominator to vanish. So that will be z is equal to e to the minus at. That seems reasonable. That's close to 1. It's on the real axis. Do we have a finite 0? Do we have a finite value of z that causes the numerator to vanish? Yes. That's a really fast 0. It's at minus 1. So that's at high frequency, which we have a high frequency 0 in our S domain. It's at infinity. What about our DC gain? Well, that's now h sub pz of 1, or that's now 1 minus e to the minus at over 2 times 2 over 1 minus e to the minus at. Well, what do you know? We have a DC gain of 1, which is how we design K. So that ugly looking expression for our pole zero matching low pass filter is actually fairly benign. It's a nice little low pass filter, and we can now implement that with a difference equation. You now know how to do all of these numerical integration strategies. Enjoy your break. I'll see you after break with shortly an exam. Enjoy your break.